Imagine you're teaching a puppy a new trick, like sit. At first, the puppy does random things like jumping, spinning, or sniffing. But you give it a treat when it accidentally gets closer to sitting. Qlearning is like that, but for AI. In this video, you learn what it is, how it works, and how to use it inside Unreal Engine to make smarter, more dynamic NPCs. Qlearning is a reinforcement learning algorithm that teaches an AI agent to make optimal decisions in any environment. The agent learns entirely through trial and error. It takes actions, receives rewards or penalties, and gradually builds up a Q table, which is essentially a cheat sheet that tells it which actions works best in each situation. The Q stands for quality, as it's measuring the quality of each possible action. The core concept resolves around the Bellman equation. But don't worry, you don't need a PhD in mathematics to understand this. Simply put, the agent learns that the value of taking an action depends on the immediate reward plus the best possible future rewards from the resulting state. Let's look at reasons for why you want to use Qlearning. Imagine enemies in your game that actually learn from player behavior. Instead of following the same predictable patterns, they adapt their strategies based on how players typically approach encounters. Qlearning can automatically adjust game difficulty by learning what level of challenge keeps players engaged without frustrating them. In strategy games, Qlearning can optimize resource allocation, learning the most efficient ways to gather, spend, and invest resources. While A* gets you from point A to point B, Qlearning can learn the best path, considering factors like enemy positions, resource locations, and changing environmental conditions. The real power lies in its versatility. It adapts to whatever environment you place it in. As with anything, there are both benefits and drawbacks in using Qlearning. Unlike expert systems that need extensive programming, Qlearning discovers optimal strategies on its own. You define the rules of the environment, and it figures out how to win. Qlearning excels in scenarios with millions of possible states, whereas traditional programming would be impractical. The agent keeps improving even after deployment, adapting to new situations and player behaviors. From DeepMind's Atari games to AlphaGo, Qlearning has demonstrated remarkable success across diverse domains. But what are the drawbacks? Qlearning can require thousands of training episodes to reach optimal performance. In game development terms, this means potentially long training times. The agent must balance trying new actions with using known good actions. Get this balance wrong, and learning can either stagnate or become chaotic. As state and action spaces grow, Q tables become exponentially large. A chess game has more possible states than atoms in the observable universe, and traditional Q tables simply can't handle this. Learning rate, discount factor, and exploration parameters all need careful tuning. Small changes can mean the difference between brilliant AI and complete failure. Traditional Qlearning struggles to apply knowledge from one scenario to similar but different situations. For this demonstration, I've created a blueprint utility actor that serves as our Qlearning trainer. This approach separates the learning process from the game loop, making it easier to understand and debug. The utility actor contains two simple buttons. One to clear the Q table and start fresh, and another to begin the training process. This gives us full control over when and how the agents learn. Our setup includes 4 critical hyperparameters that you can adjust in real time. Learning rate. This determines how quickly the agent updates its knowledge. Set it too high and the agent will overreact to new information. too low and learning becomes painfully slow. Discount factor. This controls how much the agent values future rewards versus immediate ones. A value closer to 1 makes the agent more forward-thinking, while values closer to 0 creates a more opportunistic behavior. Exploration rate balances the agent's tendency to try new actions versus sticking with what it knows works. This is crucial during the learning phase. Number of episodes defines how many complete training cycles the agent will run through. I've deliberately kept the state space minimal for clarity. Our agent has only 2 possible states. See player when the AI has detected the player. Lost player when the player is no longer in detection range. This action space is equally simple. Attack to engage the player aggressively. Search to look for the player or patrol. This 2x2 matrix creates a tiny Q table that's perfect for understanding the core concepts without getting lost in complexity. The reward structure is elegantly simple. The agent receives a reward of 1 when it takes the correct action for its current state, and 0 otherwise. In our case, attack is the optimal action when the agent can see player, and search is optimal when the agent has lost player. This creates a clear learning objective that's easy to verify. Rather than running the learning algorithm during gameplay, our training loop operates independently. This approach offers several advantages. Without rendering and game logic overhead, the agent can run through thousands of episodes in seconds. You can observe the Q values updating in real time without game distractions. Training conditions remain consistent, leading to more reliable results. The training loop follows the classic Qlearning pattern. Initialize the current state. Select an action using epsilon greedy policy. Execute the action and observe the reward. Update the Q value using the Bellman equation. Transition to the next state. Repeat until episode completion. One of the most satisfying aspects of this implementation is watching the Q values evolve. Initially, all values start at 0. As training progresses, you'll see the optimal action state pairs develop higher Q values, while the suboptimal choices remain low. After sufficient training episodes, the agent will constantly choose attack when it sees the player and search when it has lost the player, exactly the behavior we want. While our example uses just 4 possible state action combinations, the same framework scales to more complex scenarios. You could extend this to include states like player nearby, player far or low health, with corresponding actions like retreat, advance or heal. The beauty of this approach is that the core algorithm remains identical. Only the state representation and reward function change. This practical implementation demonstrates that Qlearning doesn't require complex mathematics or massive computational resources. Sometimes, the most effective AI solutions are also the simplest to understand and implement. Qlearning represents a paradigm shift in game AI, from handcrafted behaviors to learned intelligence. While it requires careful implementation and tuning, the results can be genuinely impressive. NPCs that adapt, challenges that scale, and experiences that feel truly dynamic. The key to success lies in thoughtful design of states, actions, and rewards, combined with patience during the training process. Start simple, test extensively, and gradually increase complexity as your understanding grows. Remember, Qlearning isn't just about creating smarter enemies. It's about creating more engaging, adaptive, and personalized gaming experiences that keep players coming back for more. How would you implement Qlearning, and what AI techniques would you like to see implemented in Unreal Engine? Share your thoughts in the comments. See you in the next one.